But let me say a few words about Shankar first. If Shubhasri is his first student, then in a narrow sense I am his last student, because all the other students from Vinu, Saptashi onwards, they worked with Shankar, Bhaskar and Hassan in various combinations. So I am the last solo student of Shankar. In fact, I think if you do not count the current generation of people in MSc, you must have had the maximum number of students here. Yeah, so no, because you see, we come from a different era where there were 60 faculty and 30 students. So, the number of students were much fewer. Even then, it's like in my batch at the end of first year, there were 3 of us, and all 3 of us wanted to join Shankar. But then Shankar said he's going to take 2 students. Actually, I don't think I even talked to him at that point. And it was Tarun, who is now in IIT Kanpur, and Sumitra, she is in the US now. So I dropped myself out of the race, and both of them joined Shankar. Then, so he said one problem will be in quantum Hall effect, and the other will be in quantum magnetism. Then within, I think, a couple of weeks, then both of them wanted to work in Hall effect. And then Tarun dropped out. And then I quickly, so by then I had talked to Purushottam. I wanted to work in statistical mechanics or condensed matter. And I had just talked to Purushottam, and he had left, I think, Germany or somewhere. I had talked to him just once. And then this happened, and I immediately went to Shankar and asked if he's still open to taking a student. And he said yes, and I dropped a mail to Purushottam saying that I'm switching. In fact, that is one aspect of math science which really stands out, at least in those times. All this was very easy. I think half the students ended up working with someone he didn't start with. So I think it is the most democratic place of all the places I have seen, including the West. So I don't know if it is still continuing that way. Students were really free to do what they wanted. So then finally it so happened that both of them, Sumitra also later developed interest in biophysics and worked with Gautam, and of all the 3, finally I was the only one who continued with Shankar, even though I was not there initially. So and talking of Shankar as a person, I think without exaggeration, he is the most comfortable person I have ever interacted with, and this is, I'm not saying it with any exaggeration, because with him, whatever he says is exactly what he means, as you never had to second guess. So there is something very pure and simple about him, and he's one person with zero sense of hierarchy. Zero means literally zero. So you and this has helped me now, because he had no awareness at all of the power equation between a student and faculty. And now I have to consciously remind myself how he treated me and make sure that I don't do anything using my position of power with any student. So this is one big lesson I learned from him, and that really made me feel very comfortable. And also, when somebody treats you as an equal, then you also want to do things independently. You don't always go after him for any small thing. So then initial few years, nothing much happened in the thesis. Then he said that, okay, we should really start working properly and finish things. Then there was a period of around 2 years of intense activity. In fact, Shankar would come, I mean, all the time he is in the institute, I would be with him. So he would come, most of the time he would come by lunchtime or afterwards, and then they will be working together till sometimes they will go back for dinner and come back again till early hours of the day. And I remember once a couple who is no longer here, couple told me that it's impossible to meet Shankar now without meeting you also, because and then after he leaves, then I'll go back, sleep a bit, and then complete whatever calculations we had decided on, and then the cycle will start again the next day. I want to also say one more thing. So, and I haven't met anyone who is as good as him with calculations. If there is something to do, he can just do it. So, and his lack of self-awareness is such that when you are working with him, if you are not brutally honest with yourself, you won't realize that it's he who did it. So this is something which always kept me on my toes to make sure that he doesn't run away with things, because you never realize it, because he would never make you feel that you didn't do it. So I think it was one of the fortunes of my life. I consider that I could work with Shankar, and I wish you all the best. So with that, I'll talk about something, and it will be a very general talk. Towards the end, I'll make a connection with 3D Kitai model. So topological entanglement entropy is one measure of topological order in many body systems. So this is a rough outline of the talk. I'll define what entanglement entropy is, and there's one part of it is what we call topological entanglement entropy, which is something that will be non-zero only when the system is topologically ordered. And then at the end, I'll see what this quantity means for three-dimensional systems. So entanglement entropy is just the phenomenon entropy. So if you have a system, you divide it into two, then the reduced density matrix, which is denoted by rho a here, which is obtained by just tracing out the degrees of freedom in system B. Then this phenomenon entropy of this reduced density matrix rho a, which is trace rho a log rho a. This is the bipartite entanglement entropy of system A with respect to B. Now this definition is symmetric, so because if you instead of tracing out B, if you trace out A, you will get the same thing. That is just follows from the definition. And in generic gap systems, this scales as, so in for two-dimensional systems, it scales as the length of the boundary. So in the next slide, I'll show how that happens. So to see this, so let's write the ground state wave function of the system in basis which is a product of states in A and that in B. So then this Schmidt decomposition says that you can always do it with at maximum m being the dimension of the least dimension of either A or B. At most you will need the maximal dimension of minimal dimension of A and B. So then the reduced density matrix would then have some form like this, now which is phi is only now basis states in A. So then in terms of this coefficient Ci square, the Schmidt coefficients, the entropy is just mod summation over I Ci square log Ci square. So to understand why there is an area law, This name area law comes from black hole physics, but we will not bother too much about that. So let's understand how this comes about. So if you take a lattice system and you start with the ground state, now you integrate out 1 degree of freedom. Let's say they are spins. Then so this I equal to 1 to d are the non-zero coefficients. So let's assume that all Ci's are of same order, in which case this S will be simply log d. So it's there is entanglement in d components, and then if they are all same weight, then you will get log d. Now if you do one more integrating out, then it will be log d square, and if you integrate one line, so this L is the length of the boundary here, then you will get L log d to the power L, which is L log d. So now you can keep doing that, and once you reach the correlation length, this psi is the correlation length. Now beyond the correlation, so this is a gap system, so there's a finite correlation length which is the inverse of the gap. Now if you go beyond that, then nothing further happens here, because there is no correlation between these spins and spins beyond the correlation length, in which case S is just log d to the power Lz, which is L log d to the power z. So the entropy scales as the length of the boundary. That's because there's a finite correlation length, and the spins beyond this correlation length doesn't contribute to the entropy. So this is for any generic gap system. Yeah. So now you can keep on integrating out, but it doesn't change S. So this is represented pictorially here. The contribution to entropy will come only from this narrow band around the boundary, and width of which is psi, the correlation length. So suddenly went to Now in topologically ordered systems, so let me define what we mean by a topologically ordered phase. So topologically ordered phase is where your excitations cannot be created by local operations on the ground state. So essentially the low energy excitations are, if you disturb the ground state locally, then you will be able to break them, fractionalize them, and then create the lowest excitation which cannot be destroyed by a local operation. So this is a physical definition of non-trivial phase, which is topologically non-trivial. Then in such systems, so you will have then excitations which have fractional charges and fractional statistics. Then there you can detect this topological order from the ground state itself. The properties of the excitations in some sense is encoded in this ground state entanglement entropy as a correction to this area law. So for two-dimensional systems, so if you calculate the entropy, there will be some term which is proportional to the length of the boundary. So actually area is for 3D systems, for area is a generic term here. So for 2D systems is actually length, it's a perimeter, and there will be some this correction which is some gamma times the number of connected components in your partitioning. So this is a very important result. This obtained by Kitaev, Preskill, and Wen and Levin in 2 papers that appeared side by side. So not only that, this gamma is not some arbitrary number. It encodes what is called the quantum dimension of the system. So quantum dimension is a measure of the number of different types of excitations that are there. So if for each type of anion there will be some quantum dimension, and it is just summation over root dA square. If the excitations are abelian, then it is d is 1, and it is just root of sum of total number of different type of excitations. So if gamma is 0, then that means it is topologically trivial. So just by calculating entropy and checking whether gamma is non-zero, you can say whether a system is topological or not. So now how do we extract this gamma? Because if you calculate entropy, then it is very difficult to say what scales with the boundary and what is the constant. You can put anything, and you can that way extract any constant out, but there is a way to very precise way of defining gamma unambiguously. So you can calculate this entropy for various partitionings and take a linear combination in such a way that all the boundary contribution cancel out. So this I am not going to go into why that is so, and but it is easy to see if you look at all the positive terms and negative terms, all the bulk and the boundary will be getting cancelled, and what remains will be just gamma. So now this is an unambiguous definition, and so if you know how to calculate S for one particular partitioning, then you can do this for all these given partitions and take this combination, and you can get gamma. And actually gamma is topological. You can show that if you deform these boundaries, it is not going to be affected. So it's a truly topological quantity, not that doesn't depend on the particular shape or size of the partitioning. So I'll just give one example to show how to calculate this gamma. So this is a tow record, which is perhaps the simplest model with these fractional excitations. So this is just a spin model on a square lattice. So the spins live on the links of the lattice, and the Hamiltonian is sum of two types of terms. So this AS, the star operators, are just a product of sigma x on the links emanating from each vertex, and the placket operators are sigma z from formed by each placket. Now at first sight, this is it's a trivial model, because all these AS, BP, they all commute with each other. So it is just you can simultaneously diagonalize all these AS and BP, and it's trivial to write down the ground state energy. So it would be where all AS and BP are plus 1. So both A and B square to 1. However, these all these A's and BP are not independent, and that is where the non-trivial topology comes in, because if you multiply all A's, then every sigma x will come twice, and it will be it has to multiply to 1. Similarly, all BP. So which means that you cannot create a single AS or BP. They have to always come in pairs. So this is a kinematic constraint. So those are the excitations are fractional, and one can without much work show that they have some mutual anionic statistics. They themselves are bosons, but if you exchange, if you take one type of this excitation around the other, there will be a non-trivial topological phase. So here we can check what this gamma is. So in this case, this is abelian. So there are 4 types of super selection sectors, meaning 4 different sectors. The Hilbert space divides into sectors which cannot be connected by any local transformation. So there is a vacuum with the ground state, then this E which is BP, and M is AS excitation, and one E and one M together, that will also be independent of, you cannot get any of this combination from either of any of this. So that means this D is root 4, each of this has quantum dimension 1, and D is equal to 2. So if you calculate entropy, you should get log 2, and that is indeed the case. In fact, this was calculated much before the general result of Kitaev, Preskill, and Levin-Wen, and they made the connection that this 2 is indeed the total quantum dimension of the system. Now this the proof of Kitaev and Wen, that is specific to 2 dimensions. In fact, they use conformal field theory to make the connection. Then one can ask whether this is true for 3-dimensional systems also. If you calculate this topological entropy, and does a constant term imply topological order, and if so, whether that gamma is related to the quantum dimension.
So 2D, does the constant term imply topological order?
Yeah.
Or is it both ways? Topological order implies constant term. If you find a constant term, are you guaranteed that
you are, because that constant term is log D. Yeah. So D has to be non-zero. No, it has to be greater than 1. Yeah. Now it turns out that in 3D, a constant term doesn't necessarily mean topological order. Now, so there's a very nice paper by Tarun Grover and et al. So what they have shown is that if you can think of entropy as a sum of local terms coming from different patches of the boundary between the 2 partitions, then they have used this symmetry that SA equal to SB and shown that see, in even dimensions, this entropy can only depend on odd powers of L. So in 2 dimensions, it will be, the leading term will be L, the next one will be not L to the power 0, but 1 by L, and so on. So then in odd dimensions, it will be powers of, sum of powers of even powers of L. So L square, the area term, will be the leading term, but so in 3D, then the correction would be the next term is L to the power 0, the constant term. So this can come from local contribution. So you don't need topologically ordered phase to get constant term. So that in itself, if you calculate entropy and get a constant term, that doesn't necessarily mean that you have fractional excitations. However, you can still extract topological entropy. You can define again an unambiguous quantity which is topological by generalizing this partitioning scheme that we saw earlier in 2D, and that way we can still define a gamma and calculate it. So then we ask whether this gamma is still log D, and that is true for a variety of 2D systems exactly solvable where you can calculate it. Like the Tori code, there is a generalization to 3D. Then there are so-called quantum double models defined for a general gauge group G, and what are called Walker-Wang models. In all these cases, this still holds. You calculate gamma, it is still log D. But it turns out that that is not the case for the three-dimensional Kitai model. Now, I want to give a little bit of history about Kitai model. Actually, Kitai did this work and published it, I think, years after he did the work. So here Shankar and Bhaskaran and Saptarshi, they started working on it, I think a couple of years after I had left. And I think Bhaskaran had listened to some talk of Kitai somewhere, he got the slides, and that is how I think they started. So they were one of the early birds in the field. Then, if I remember right, I was in IISc Bangalore, and Shankar once gave a talk there, and that is how I learned about Kitai model. And then from IISc, I had gone to, I was in ICTP, and as a postdoc, and Saptarshi once was visiting there, he was attending a school. And I had this idea about the 3D generalization, and I talked to him, and we then started working on it. In fact, Shankar and Bhaskaran were also involved initially, but then later then they asked us to do it on our own. So, yeah, so I think all this Saptarshi has already talked about the 2D model. Then we came up with this lattice in 3D where all the exact solvability of Kitai model generalizes. And as I said earlier, then one has to come up with a scheme again to get rid of all the effects from the boundaries and corners and so on to extract this gamma, and that can be done. And you get the same log 2 for gamma, but now this quantum dimension in the 3D is not 2. So it's not so easy to see what the quantum dimension is if you look at the spin model, but you can look at one limit of Kitai model, which will again, if you this is the so Kitai model has a gap phase as well as a gapless phase. So in the gap phase, if you take the limit of one bond being very strong, then you can map it to a Torrico type model on the diamond lattice, which can be studied easily. And this model has only two superselection sectors. It has some complicated loop-like excitations, which are fermions, and those are the only non-trivial excitations other than vacuum. And D is root 2. So gamma is in this case not equal to log D. So yeah. So actually this work was calculation was done with the student Randeep, who is in IIST. So this is just a summary that the topological entanglement entropy gamma gives a measure of topological order, and gamma has a very precise meaning in 2D, which is related to the quantum dimension of the system. And what we have seen is that in 3D that is not always the case. And what exactly is the relation between D and gamma in 3D is not very clear. So I think that is still something to be explored. Yeah, that's it. Thank you.